welcome to the session. So in this particular video, we will talk about the implementation of QuickSort. So until so far, I hope that in the previous video, whatsoever things I have discussed related to the QuickSort, whether we will talk about the logic behind that, we will talk about the recursive tree, we will talk about the recurrence relation, all those aspects will be pretty much clear to everyone, right? Now, I'm also expecting from everyone that you already have tried at least once, because I already gave you the pseudocode for the partition algorithm as well as the QuickSort to implement that. And I will humbly request to everyone that before coming to this session or before watching upcoming part of this session, please, if you haven't tried it yet, try to do it on your own first, right? After that, might be there are many people who might be successful in getting a result, but there are few people who will be suffering. You don't need to get motivated by that, demotivated by that. You just need to see after unpausing this video that where you are doing something wrong. Even maximum number of times while doing the live implementation, I also might get stuck, right? At that point of time also, my major objective is to see that where is my mistake, and from that mistake only I would learn, and in the future I will not do those kind of mistakes, right? This is the way to learn only, right? So specifically talking about coding, the more you do, the more you will get the confidence, the more you will be able to understand the concepts behind that. Okay, so let's get started with the implementation part now without any delay. So here, if you will see, we will be having, let me write the driver code first. So in this driver code, let me talk about the array. So let me take some random unsorted array, for example, 20, 10, 5, 70, right? 50, 89, 34, 47, like that. Now, after this, we will be having the value of p, which I am stating as a starting index is equals to 0. And the value of q, which is equals to length of the array that we have, minus 1, right? Now, we will just call the function, namely QuickSort, and inside that function, what I will do is that I'll try to store this array r, I'll try to store the starting index p and the ending index q. And then I can print this particular result by saying that sorted array after applying the QuickSort is, okay? Now here what we can do is that we can simply print the result. So here is something where the function calling naturally happened, right? Now let's talk about the function definition of QuickSort. Function definition of QuickSort, which we have called. So here the function name is QuickSort. Inside that we will be having the array, we will be having the starting index and the ending index. Now what we can say is that if the value of p is less than q, do one thing for us. Now here we need to call that partition function to determine the mid value. So here mid will not happen like the way we used to do in binary search or in merge sort that we have already discussed. So here the mid value will be something where we are calling a partition algo, which will again take the value of array, p and the q. And now what we can do is that we can simply call the function named as QuickSort, and inside that we can pass the array r, we can pass the value starting index p and the value mid minus 1. Similarly, the next right side recursive call will go until mid plus 1 to the value of q, right? And finally, we can, when we will be out of this recursive call, we can return the final sorted array. Now, here is the function calling, I would say, for the partition algorithm, right? So we need to define that. And here is the something which you can say is the recursive call for left subtree. And here is something which we can say is the recursive call for right subtree. Now let's talk about the function definition for the final thing that is left, which is the partition algorithm. So let's talk about the function definition of partition algorithm. Here what we can do is that we can define partition algorithm. Inside that we can define the value of P and the value of Q, and here what we can do is that we can say that initially the value of I is something which is equals to P, and the value of what I can say pivot is something which is equals to what is the value of R of P. Means we are considering the starting element in an array as a pivot element. Here you have the option, or you have the liberty to choose the ending element or any random element as well. We will talk about this thing in very much depth in a separate session, but let's talk about in today's session the starting element as a pivot element itself, because this is the only thing that we have discussed in the last session itself, right? Okay, once this thing is done, what we can do is that we can start one for loop which will start from the value of I plus 1 and will go until the value of Q plus 1. Now what we can do inside here is that we can say, because the responsibility of this J is to take the larger elements than pivot. So if this J will be able to get the element R of J is somewhere less than equals to the pivot element that we have, at that point of time what we can do is that we can first of all increment the value of I by I plus 1, you can say like this, and then you can swap the value of R of I with the value of R of J. This is what we did, right? So this is what will happen here as well. And finally, once we will be out of the for loop, there will be a final swap between the R of I and the pivot element. So majorly what we can do is that R of I will get swapped with the value of R of P, which is the pivot element that we have, and R of P will be R of I. So this is how basically swap will happen. Internally we did the swap between the R of I and R of J. Now once these things are done, what we can do is that we can simply return the value of I, right? That will indicate the index number of an I. If I will run this code and we'll try to see, so I think we are getting a sorted array which is 5, 10, 20, 34, 47, 50, 70 and 89. So it is going back. So let me remove one element. Let's see now. So now here you can clearly see that we are getting a sorted array, right? All these things are done how? With the help of a QuickSort algorithm. So here we did the implementation using the QuickSort algorithm, right? Now if I will talk about the time complexity of partitioning algorithm, if you will observe here just one for loop is running inside that, right? This is something in worst case you can say as big O of n, right? And here if you will see the recursive call it is taking, so it will be T of how many number of elements do we have? Mid minus 1 minus P plus 1, so you can say T of mid minus P, and here it will be just like the way we have discussed in our last class also. So coding wise also I am discussing the same thing. It will be Q minus mid, can I say? So the overall recurrence relation, if I will talk about the recurrence relation of this code, you can say like that. So recurrence relation will be something which is equals to T of n, which is equals to T of m minus P plus T of Q minus m plus n. Now here you can easily talk about the best case scenario. In best case scenario, your recurrence relation will be formed like T of n, where, so best case scenario meaning half of the elements will be at the left subtree and half of the elements will be at the right subtree. Means the element which is the index which is returned by this partitioning algorithm will be just at the mid, right? So at that point of time, your value of T of n will be T of n by 2, half of the elements at the left subtree, and half of the elements are at the right subtree plus n, which will give you the overall time complexity as big O of n log n. But when you are talking about a worst case scenario, at that point of time, what will be the time complexity? It will be something where you can say that maybe 1 or 2 elements are at the left side, but all other elements are on the right subtree, and vice versa, where all the elements are on the left subtree and maybe 1 or at max 2 elements are on the left subtree. So at that point of time, your recurrence relation will look like T of n minus 1 plus constant plus n. So if you will solve this recurrence relation, you will be able to get the result as big O of n square. So one thing that you need to take care in your head is that whenever we are talking about a quick sort, never ever be in a situation where you will go for worst case scenario, because then this quick sort is not a good choice, right? And when will it happen? We already have discussed that this kind of situation will happen when you have a already sorted array or almost sorted array, and then you are applying a quicksort kind of algorithm. At that point of time, you will observe that you will always be in this particular situation. And in the last session, I gave you the example proof of that as well, right? So with this, I hope that I'm making sense to everyone, right? The implementation part of the quicksort is pretty much clear to everyone. I'm expecting so. If you still have any sort of doubt, do let me know. I will for sure try to resolve it as soon as possible. With this, happy learning to all. Bye-bye everyone. I'll see you all in my next upcoming video, where now we will talk about the technical interview based questions which can be asked from you in an interview on the basis of this quicksort knowledge that you gain, right? So I hope that you all are enjoying this course series of DSA, right? Bye-bye everyone. See you all in my next upcoming video.